Hi everyone, welcome back. We've spent all this time on models that talk, that answer, that generate, and that are brilliant at all of these. But they're passive. That is, they wait for you. This block is about turning that passive model into an agent, something that can actually go and do things. And it comes down to three capabilities: tools, memory, and a protocol called MCP that connects them. Think about it. What actually separates an agent from a chatbot are these very three things: tools, so it can act on the world; memory, so it can persist across time instead of forgetting everything; and a protocol, so it can connect to the tools without a custom integration required each time. Let's get started. Coming to the most fundamental one, which is tools, and to motivate it, think about what a language model literally cannot do on its own, no matter how smart it is. The first one is the knowledge cutoff, because these language models are trained at some point in the past. So they simply cannot say what has happened today or have the present facts with them. The fix here is to give them a search command or search tool. The second one is that they're really bad at compute, and you can actually try it on your own by asking an LLM to multiply two big numbers or run a long calculation. It's bound to fumble, and it's going to predict digits instead of calculating it. The fix is you give it a calculator or a code sandbox. The third one, and this is the big one, it can't act. Basically, it's text in and text out, and it can't touch a file, hit an API, or click a button. The fix: give it tools, a file system, and a browser, or many APIs. And the fourth one is accuracy. Even when it could guess, a real tool is going to be very exact. A database query knows the answer, but instead the model is just predicting a plausible one. So here's the contrast between a model plus tool combination versus a model alone. And let's take an example for this whole block. And like a code agent that fixes bug. Let's take this example and think about it. That agent can't fix a bug by describing the fix in a nice paragraph. It has to actually open the file, edit it, and run the tests. Hence, talking or generating text isn't enough. It needs tools. And that's the entire point of this. Okay, so how does a model that only outputs text actually call a tool? Because that sounds kind of like a contradiction, right? The first thing here is that you declare your tools to the model. Each one gets a name, a description, and a parameter schema. Here's a tool called run tests. And what it does is that, and you then describe what it does and what are the arguments. The second one is that the model needs to select these tools. And for this, it has been trained on tons of tool use data. And so instead of writing prose, it emits a structured call. Basically, it just says call run test with these arguments. And it's not running anything, it's just asking. The third one is the most important one, and basically people miss this a lot, is that your code executes the tool. The model is not going to run anything by itself. The harness, your code, sees the request the model has given and actually runs the function and gets the result. The fourth one is that the result goes back into the model's context, and it reads and then decides what to do. And then the loop keeps on repeating. So for the example of a code agent that we took, it asks to run the tests. Your harness is going to run them, and the failures are going to come back to the model as context, and the model is going to read them and then decide on what files to edit or what changes to make. So the whole pipeline is ask, execute, observe, decide, and this continues together. Now, one of the refinement that matters a lot for speed is that the model doesn't have to call tools call all the tools one at a time. And we can see this by an example. When tool calls don't depend on each other, the model can request them to run parallelly all at once, and your harness is going to run all of them at the same time in parallel, which is depicted by the top example. And you can see that all of them finish in one round trip. Now compare it to the bottom example. Um, Basically, if you did those three same calls one after the other sequentially, it's the three times the weight, assuming that each tool call takes roughly the same amount of time. And Let's continue with the example that we took. Our code agent wants to understand a bug. So it reads three different files. And if those reads don't depend on each other, we can do all three of them at once in one round trip and the latency collapses. And this is an important but, that is that if call B needs the result of call A, say that basically the code agent says read a file and then basically it needs to edit it based on what the agent has read, the model is going to keep those sequential. And the nice part is that the model is going to wait and the model is going to figure out on its own that which call is sequential and which call can be done in parallel. And the best part is that each of these calls are emitted as a schema constrained JSON. So the arguments actually parse every single time. And so here's a particular lesson that everyone in the field took time to appreciate. And it's basically seen on the code card. When you give a model tools, the schema you write is the prompt. The model learns which tools to call and with what arguments purely by reading your descriptions. So you have to write them as you were writing for a reader and not like just for yourself. Look at the weak version up there, a tool called get. Description gets data and one param q, which is of the type string. The model has no idea when to use this or what to put in queue. It'll guess and maybe guess the wrong thing. But look at the other version, which is the good version. The name says what it does: search orders. The description is written for a human, which says that finds a customer's orders by email and use this for where is my order question. The parameters are very specific. Email is a required parameter, and status is kind of an enum. And this helps basically the model to have a very clear and crystal view of that particular tool. So the principles here are clear descriptions because the model needs them to choose, and basically minimal required parameters because every required field is another chance to fail. And enums instead of free text wherever you can, because honestly, putting examples right in the description uh, helps like it measurably improves how well the model picks. And basically treat your tool schemas like prompt engineering because that's what exactly they are. They need to be really structured and really tailored for the task at hand. Um, so far, so good with just a handful number of tools. But what happens when your agent has hundreds of thousands of tools available? The model can't reason well over a giant menu, and stuffing every schema into context is really expensive. So, three strategies come to our rescue, and the chart shows how they are going to scale. The first one is that you just let the model choose and dump all the tools and just let it pick. Simple and most common, and totally fine for up to a dozen tool calls. But watch the orange curve. As the toolbox grows, cost and error rate blow up literally. The second one is a router. Basically, you have a cheap model that classifies the intent of all the utterances that are coming. So let's say this is a billing question, and then you only expose the billing tools to the main model, and the curve is going to stay much flatter. The third one is retrieval, wherein you treat your tools like documents and embed every tool description, and for each query, you just fetch the top K most relevant ones. And look, that it's going to stay the flattest of all because it barely cares how many tools exist. And because by design, it is going to just surface a handful of them after retrieval. The takeaway is that the naive approach is fine until it isn't. That is like post the tool calls are beyond, let's say, a dozen tools. And as your toolbox explodes, you need to either route or you need to either retrieve. And so basically, here's something that separates a toy agent from a real one, and it's handling failures. So tool fails constantly in the real world, and networks are going to time out. APIs are going to return errors, and arguments come out malformed. A brittle agent just dies, and the good agent treats a failed call as information and context. So basically, there's a clear escalation ladder. If execution fails, first retry and look that if it's transient, is it a network blip or is it failing persistently? Then try a different tool that does the same job. And if it's still stuck, then ask the user. And it's going to happen in that order, cheapest and the most automatic first. And in case of malformed parameters, don't crash. Just feed the validation error back to the model. It's going to read that as basically, hey, that argument was wrong type, and it's going to self correct on its own. And that feedback loop is very powerful. You also need to always put a timeout on every call so that one hung tool must never hang the whole agent. And finally, you should have grace for degradation. Basically, if you can still give a useful answer without the tool, you just need to do it and just be honest that you couldn't use the tool because it wasn't available or it was hung up or there were some API errors or something like this. And basically, I wanted to notice that the recovery pattern comes back. The multi-agent retries and the production backoff you'll see in the later blocks are based on the same idea, and they are just the scaled up version of this. Before we leave tools, a serious word on security, because it's easy to forget in all of this stuff. And here's the framing that I want you to remember. Every tool you give an agent is a hole that you've punched in the sandbox, and it's basically an attack surface. So the rule is grant the least that works. Um, and there are three principles you need to remember. The first one is least privilege. Give each tool the narrowest scope that does the job. So basically, a tool that only needs to read should never be able to write. The second one is allow listing. And basically, you need to name exactly which tools an agent may call and which tools the agent should default to deny and not allow. And the third one is human in the loop. For anything destructive or irreversible, such as deleting data and sending money, the agent pauses and a human approves. Um, okay, let's move to the section two of this block, which focuses on memory after section one, which was on tools. And here's the problem it solves. And I'll state it as bluntly as I can. Basically, an agent is going to forget uh, and is going to restart from every single turn. So basically, we don't want this to happen wherein the agent is going to forget the last conversation and then start from scratch in the like sequential conversation or the consecutive conversation. And you can watch these two curves, and they are how much work gets redone over a session. The orange one is a stateless agent with no memory. And you can see how it just keeps climbing. Every turn, it's going to rederive everything that it has already figured out. And the worst part is it repeats the mistakes it has already made. And it's really exhausting and expensive. The blue one is an agent with memory. It flattens out because it builds on what it already knows. Now, an important distinction that people get wrong is that context window is not memory. Yes, it's large, but it's bounded and it's going to fill up and it's going to vanish the moment the session is going to end. Real memory means persisting what matters so that the next turn or even the next session starts ahead instead of starting from scratch. And the whole discipline of memory is three verbs: store the right things, recall them at the right time, and drop the rest. That's it. Everything in this section is basically going to surround how to do all of these three things very well. So coming to memory, memory isn't one thing. It's a hierarchy, and it's sorted by how long it lasts and where it lives. So basically, you can see there are four tiers. The first one is working memory, which is the current context window, your conversation, and basically your conversation and a scratch pad for immediate results. And it's very fast and right there, but it's really bounded. Then there is short-term memory within a single session. And as the conversation picks up and gets long, you summarize the older parts and keep the key decisions. So it survives the context compaction. Then there is long-term memory across sessions. This is where user preferences and learned facts live. Basically, stuff like this user always wants, TypeScript or not JavaScript. And this memory lives in an external store, which is a database, and it's always there. And the last one is that is episodic memory, and which is memory of past experiences. And this is a really interesting one because it stores the past experiences. And think of it using an example. Last time I tried approach X and it failed because of Y, and that's a reflection style, storage, and that is what we are going to discuss next. So let's zoom in on episodic memory. because it's genuinely really powerful, and it lets an agent learn from failure without any retraining. So you can follow the loop that this slide has. The first attempt is when the agent is going to try to, fix a bug. It is going to fail, and the tests are going to go red. And instead of just blindly trying again, it's going to reflect. It writes a short note to itself that I failed because I forgot to handle this case, or I forgot that argument or that tool call, and that's called reflection. And basically, this little lesson is going to get stored in episodic memory. Then on the retry, you can see that basically the lesson gets pulled back into context before attempt two, and the agent goes in already knowing what not to do. And then in the attempt two, it is informed by the failure, which was living in the episodic memory. It avoids that and it succeeds. The tests run green. Basically, the idea here is that the agent got better between attempt one and two, and without even us touching any weights or you doing any retraining or fine tuning, because it just remembered its own mistake and it didn't repeat it. That's the difference between an agent that keeps on banging its head on the same wall forever, and the one that actually gets somewhere by ignoring these walls. And you can notice that this is exactly the star and the self improvement idea from the alignment block. Basically, building on the same principle of learning from your own filtered experience. And that's just happening here in an inference time. But the question is that how do you implement memory? And there are four common patterns. Each of those will trade off recall quality against cost and complexity. So the first one is vector store, wherein you embed everything the agent has seen and retrieve by semantic similarity. And this is the best when you have questions like, "Oh, have I seen something like this before?" Then you move to sliding window plus summary memory, wherein you keep the recent turns word for word and compress the older ones into a running summary. It's simple and effective. Then there's structured memory, when you pull out entities and facts and store them in a type store. And basically, it contains stuff like, this is the user's name, it's their plan, it's their preferences, the relationships that they have. And this structured memory is exact, variable, and has no drift. And basically, it stores the user profiles, the user preferences. And the fourth one is hierarchical, wherein basically it has details of the recent past, and it is fuzzy and abstract for the distant past, which is honestly roughly how human memory also works, right? Like we have a approximate understanding of the very old past events, but we have detailed, or like we remember the recent experiences very well. And the idea here is that you'll often need to combine all of these. Basically, a vector store for episodic uh, recall plus structured memory for hard facts is a really common pairing. And there's no single right answer here, and it depends on what your agent needs and how it needs to remember it. And basically, memory that you never curate becomes just noise. And basically, it then becomes a giant pile that the agent can find anything in. So here are four operations that need to be performed from time to time. The first one is write, which is like decide what's even worth keeping. And the keyword is not everything. Most of what happens in a turn is disposable. The second one is read, which is surface the right memory at the right moment. And notice that's fundamentally a retrieval problem. The same retrieval you saw for tools and for app. The third one is update. That is when a fact changes, revise it. The user switched from a free plan to pro, and is one of such examples. And the last one is forget, which is actively removing what's wrong or what's outdated. And yeah, this is the conclusion of how you need to handle memory. And basically, there are three things that I like to call out, and you should watch out for them. The first one is curation, knowing what to keep versus just tossing everything out. The second one is relevance, which is like pulling the right memory at the right time, and again, it is like retrieval. And the third one is staleness, and like basically, this says that the world is going to change, but memory is not going to change unless you make it change. So a memory that says that the user lives in Seattle, even when the user has moved, is much worse than a memory that does not have that information. So yeah, these are the three caveats that I'd like to make here in this memory part of the deck. Now, after tools and memory, we have MCP, which is the Model Context Protocol. And to get why it exists, we need to actually think about the problem that it's going to solve. Before MCP, you can look at this mess. Every model has to integrate every tool by hand. So there are n models and m tools. That's n cross m times these spoke connections. And it's worse than the number suggests because every single tool has a different API, a different auth flow, a different parameter schema, and they are not just going to compose together. You're rewriting the same integration over and over because of this. Here comes an MCP, and this collapses. So MCP is like a universal protocol with one standard wire format. The analogy everyone uses is USB-C. Basically, you need to think of the time when every device had its own charger. So you had Motorola and BlackBerry having different charger pins. You had Samsung having different charger pins, and you need to buy these pins like whenever you change your phone. But then came USB-C, which was like a one standard connector. And this is exactly the same thing that once you build a tool um, as an MCP server or any MCP, like once you build this tool as an MCP server, any MCP compatible host can use it or run it. So this n times m becomes n plus m, so wherein like there are m is the number of servers and n is the number of hosts. So and all of these just have one protocol between them. So you collapse from n cross m to n plus m. That is like from a very entangled mesh to a clean hub that USB-C or MCP provided. Now, what are the actual pieces of MCP? And there are three roles with really clean separation. The first one is the host, which is the app that you actually use, and these are your ID or a chat client or basically an agent that like a code agent that we've been discussing. The second one is client, which lives inside the host and is going to be one per server, and its only job is to speak the protocol. And the server is the thing that expresses the capabilities, which is the tools and the data that the client has. And here's the beautiful part of this separation. Because like a team can build and ship an MCP server without touching any model at all. The database team ships a database server. They don't know or don't really care whether you're using Claude or GPT or Gemini. They just speak MCP. And basically, your host sends a request through its client to the server, which hits the actual tool or data, and the result flows back. So, host, client, and server uh, this is the MCP pipeline, and all of these are decoupled from each other. So the tool builders and the model builders will never have to coordinate with each other, and this is how the whole ecosystem is able to scale. And so basically, an MCP server exposes many capabilities, but there are exactly three kinds. And the distinction actually really matters because we need to see who's in control. So basically, tools, which are the callable functions with schemas, uh, and basically what we have been discussed in the first section also. The key thing is that tools are model controlled, and the model decides to call them, run the tests, edit the file, and all of these are decided, and the sequence is decided by the model. Then comes resources, which is readable data, your files, your API responses, and database rows, and these are application control. Your app decides what data to feed in. And let's say for our code agent, the source files are resources. The third one is prompts and reusable prompt templates that the host can offer to the user. Things like slash command or like, slash review PR, slash summarize, slash deep research. All of these are user controlled and the user is going to trigger them. And basically, the whole mental model is that the model picks these tools, the app provides the resources, and the user fires of prompts. And notice that behind all of these three parameters, there are three different parties in control. And once you see the split, MCP servers, are stop going to be mysterious to you. They are just really simple and about what is like who is controlling what. Now coming to ways to reach a server, there are two transports or two ways you basically your host is going to actually talk to a server, and it depends on where it's going to live. So the first one is STDO, or basically you can call it's an acronym for standard in and out. And the server is a local subprocess on your own machine. The host is going to just launch it and talk to it over a pipe. It's really simple, it's fast, and it's private, and it's perfect for local stuff, your files, your Git, and your own scripts. The other is HTTP with server sent events, or streamable HTTP. Now the server is on the network, and it's possibly remote, and it's going to be shared by many users. So it's for hosted multi-user SaaS style tools. And um, the point here is that your agent code does not change between them. Swapping a local tool for a remote tool is just a config detail, and you don't need to rewrite anything. So there's the same protocol, but a different pipe. And this is the payoff of having a standard protocol or a structured way of communicating between these tools. So why did MCP actually, impact our LLM systems the way it did? And basically, there are like the benefits coming from the idea itself, and then coming from the whole ecosystem, and how the ecosystem has responded to it. The benefits list is basically like MCP allows us to just build once, and then it works with any compatible host. And that's a really big advantage. The second one is discovery. Basically, an agent can ask a server at runtime, what tools do you have? So it does not require any hard coding, and tools can appear, as a menu, and the agent can just find them. The third one is composability. And this is basically chaining several servers together. A file system server plus a database server plus a browser all at once. And the last one is capability based security. The host grants only the access it means to. So this is what the whitelisting part that we talked about earlier. And then let's move on to the ecosystem. So MCP was created by Anthropic in 2024, but crucially it got adopted by OpenAI, Google, Microsoft, Amazon, like basically the competitors. And basically there are now, thousands of community servers, and it's built natively into tools like Claude Code, VS Code, and JetBrains. So the rule about standards is that a standard wins when building to it is easier than building around it. And MCP basically crossed that threshold. And basically, the idea is that once your competitors start adapting your standard, it has real impact. Um, so basically, there is a common misconception that MCP is like function calling, but they are related to each other, but they are really different layers. And I'd like to show this comparison to sort things out. Function calling is a mechanism. It's model specific and baked into one provider's API. And basically, you wire each tool yourself. It's how a single model in a single app calls a tool. And we've covered it extensively in the initial section of this module. MCP, on the other hand, is an ecosystem around that mechanism because it's model agnostic, and it sits at the protocol level, and the tools are discoverable and composable across many hosts. And here's the key: they are not competitors, but they are complementary. Under the hood, an MCP host takes the tools it has discovered and turns them into ordinary function calls for whatever model it's using. So MCP is kind of feeding function calling. And the rule of the thumb is that if you've got one model and a few fixed tools, function calling would work very well for you directly. And MCP would rather be an overkill here. But if you've got too many tools and you want to work across many hosts, that's exactly when you reach MCP. And basically, just remember that the right tool is related to the right scale at which you're operating. And here's a recap slide. So basically, let's pull everything together, and let's see what all we've discovered through this module. With tools, the model can now act. It can read files, run tests, and edit codes. It fires those tools in parallel, and when one fails, it recovers instead of dying using the reflection thing that we talked about. With memory, it now can persist, experience and knowledge it has acquired, and it remembers which fixes it already tried and what failed and why. So it's going to stop looping on the same dead end, and it gets better within a task and across tasks. And with MCP, it now connects everything. That same agent reaches GitHub, your file system, any database that you wanted to reach, all through one clean protocol instead of a tangle of custom integrations. And basically, um, tools to act, memory to persist, and a protocol to connect. This is what encompasses a capable agent. But notice one thing, that it's still one agent and it's going to work alone. And that's the perfect setup for what we have next, which is how do this one capable agent become many capable agents coordinating through workflows and multi-agent systems.